Okay, hello, welcome to the second tutorial of the course Magnetism and Superconductivity. And in the last week's tutorial, we discussed some problems that are related to the week 1 lectures. And similarly, in this week tutorial, we will discuss some more problems which are related to the topics that are covered in the lectures of week 2. And as I told you earlier that I will not be solving the direct assignments that you are given as a part of graded assignment in the course. I will only help you solve that, or I will give you ideas if you have some doubts in the solution only after the deadline of submission of each of the assignments. So like for week 1 assignment, I think the deadline is still not over. It is 7th of August and today it is 6th of August. So we'll not discuss that assignment right now, but rather I will focus on some problems that are related to the next week's lectures, like week 2 lectures, so that you can get an idea and get help in solving related problems of your week 2 assignment. Okay, so I hope you can see my screen, everyone, and so I'll begin. There are 10 problems in this assignment, and I'll one by one solve them and explain those to you. Okay, so okay, let us look at the first question. It says that the adiabatic demagnetization is a particular method of cooling which capitalizes on the what properties of material. So we have to fill in the blank in this place, that the adiabatic demagnetization is a method of cooling that we know, or we probably know that it is a very famous method of cooling down to really low temperature. Especially you can go down to millikelvin range in this method, and that is why it is very useful in superconducting materials, because to go you can, using this temperature, you can go such lower temperature range. So that is obviously in some materials you can go to the superconducting temperature range of those materials which have very low TC value. So now this is a cooling method that we know, but what is asked in this question is that on what property of materials is the cooling process dependent on. So I'll first tell you the answer. The answer is that it is dependent on the paramagnetic property of materials. So and why that, why so, like why it is dependent on the paramagnetic property of materials, that I'd like to elaborate a bit. So let us go to a blank page and explain the process first. Okay, now I am only explaining it to you, the process of adiabatic demagnetization, because I think it is a very useful and interesting topic to cover, in the sense that I feel it is some process that involves both of the fundamental like starting points of this course. Like this course is all about the concepts in magnetism and superconductivity. So adiabatic demagnetization is a process that includes both of them together. Like it can help us go to really low temperature by cooling, and for that cooling mechanism it uses the magnetic property of matter, which is in this case paramagnetism more explicitly. So basically it involves magnetism and also very low temperature, so basically in the superconducting range of some materials. Okay, so that is why it is a very interesting method that I want to discuss and explain to you. So we will cover that slowly. Let us begin then. So we want to talk about a bit about adiabatic demagnetization. Okay, first of all, what is this process? So it is basically a cooling mechanism. It is basically a cooling process, can help to reach even millikelvin temperature range, some order of millikelvin, let's say millikelvin temperature range, but your starting temperature should be in the 1 to 5 Kelvin range. And I mean, you have to be first at an initial starting temperature of some 1 to 5 Kelvin range, and only after that you can use this adiabatic demagnetization process to cool the sample down further below. Okay, So this is one thing, that the starting temperature in this process should be in this low regime of 1 to 5 Kelvin. You cannot start with 300 Kelvin and try this demagnetization, adiabatic demagnetization process to go down further. It has the starting condition that you have to be in a temperature range of 1 to 5 Kelvin, and only after that this process can work to get you to further lower temperature of millikelvin. As I said, that it has capacity to reach millikelvin range. Now, the basic thing that you require for this process is that you need a paramagnetic salt sample. Okay, so your sample should have the paramagnetic property. That is why in this question, MCQ question, we had this option of paramagnetic that I said will be correct, that it is dependent on the paramagnetic property of material. If your sample is non-magnetic, it will not work. Okay, and even if it is diamagnetic or whatever, it will not work. It will only work only if the sample is paramagnetic. So your sample should be a paramagnetic salt sample. So salt is basically not, it is not a very crucial fact, only the paramagnetic property matters here for this process. But mostly in these cases, the samples that are used for these cases are paramagnetic salt samples. Okay, so basically there are separate mixture elements of materials that are used as paramagnetic salt, that I'll give an example later. But the sample is a paramagnetic sample, that is the first thing. And if we just briefly in one line want to discuss what is the principal mechanism based on which this process works. So the idea is that the system here, which is a paramagnetic system, is made to do some magnetic work. Okay, so you know the work done can be defined as P times dV, right? Like you know the work done, dW, can be P dV, where P is pressure and dV is the volume change. So this is basically the work done involved with the change of volume. So this is not some magnetic work done. Similarly, in work dimensions, you know that it can be expressed in an analogous form as HdM, where H can be thought to be equivalent to or analogous to pressure, and M, this magnetization, this quantity, can be thought to be analogous to the quantity of volume. So this is the analogous expression of same work done, but in this case it is a magnetic work done, because all the magnetic terms are involved in this. I mean, magnetic term, by magnetic terms I mean that here this is H, so H is the magnetic field, you know, and M is the magnetization of the material. So this is basically a magnetic work done. Okay, right. So this is the magnetic work done, and so basically you force the system to do a magnetic work. You set up the configuration like that the system does a magnetic work, and to compensate that work done, the system's internal energy actually changes. So basically the system's internal energy decreases, or in other terms the system actually cools down, or its temperature decreases when it is forced to do a magnetic work, and the work is like in this case compensated in terms of the system's internal energy, because the process is adiabatic. So adiabatic means you cannot have any heat exchange DQ part with any part of the environment whatsoever. So the only way for you to compensate for the work done of the system, the magnetic work done in this case, is to change the internal energy of the system. So in the cost of internal energy of the system, you decrease the system's temperature and can go down to millikelvin range. So the basic mechanism is, let me write it down. Basic mechanism is get the system to do magnetic work done, magnetic work, which is nothing but the work of HdM in this case, as I have shown you earlier. Okay, so let me check. So the basic mechanism is to get the system to do magnetic work, and this is one part where the magnetic work is HdM. Okay, under adiabatic condition. So the work done is happening under adiabatic condition. That means your system is completely isolated from the environment, the adiabatic condition. So your dq is 0. That means no heat exchange is allowed with the system and the surrounding. Okay, and so the work done is compensated at the cost of the internal energy of the system. Internal energy, which is the change in internal energy, in this case is du of the system. And you know that if the system's internal energy is getting affected, that means the system temperature will also be dependent on that, will be getting changed. Okay, so that is why temperature of the system reduces and you get the cooling. That is why you get the cooling. So this is the basic mechanism as I am explaining to you. And if we just want to go a little deeper to just understand the general principle of this method and what is the general setup, design, and some part of what is the expression that is involved with the temperature change equation in thermodynamics, I'll just get into that very briefly, but actually it will be helpful in understanding the concept better, so I think I'll cover that. So let us say that we want to know the general principle. I mean, what is the general idea behind this? Not specific for the system, but general idea. So the basic idea that comes into our mind is that there is an entropy picture that is involved here. Okay. So you know that entropy is something that describes the randomness of a system. You can say that it explains why if the system is more ordered or more disordered. Randomness means the system is more disordered, right? So entropy is some kind of a measure of the randomness or disorder in a system. So naturally, if you have entropy in the y-axis and temperature in the x-axis, so in lower temperature, system will be more ordered. But as you increase the temperature, there will be more thermal fluctuation, more disorder introduced to it, more randomness because of thermal energy, right? So obviously the entropy will then increase with the increase in temperature, because the randomness will increase, disorder will increase with increasing temperature. That is why entropy will also increase like this. Let's say we draw it. So it will increase first, and then after some point it will be saturated like this. Okay, so this is for, let's say, at zero magnetic field, when H equal to 0, there is no magnetic field present, then the entropy initially increases with temperature, because the disorder or the randomness in the system increases with temperature increase, and then it eventually gets saturated after some time. Maybe the saturation comes after a significant enough temperature range is covered, maybe not so soon, but it is just a graphical representation that I am doing, so do not take it absolutely as in the exact scale. Okay, just get the idea that initially with increasing temperature entropy will increase, and then after certain point it will get flattened out, because then whatever temperature will increase in the system's disorder has already saturated because of that. Okay, so this is the scenario, but this is for H equal to 0. That means your there is no magnetic field that is present. Okay, otherwise, when let's say you have applied a magnetic field also, then how should the entropy behave with temperature? So then it is seen that the entropy behavior for a finite magnetic field will go like this now. So this is for H equal to H1, where the field is non-zero. H1 field is non-zero. H1. Okay, so basically what is happening is that, first of all, if temperature increases, thermal instability of the system increases. Thermal instability causes the disorder to increase, and that's why entropy to increase, and eventually get saturated at a higher temperature. Okay, that is fine, but this is the case for H equal to 0, when there is no magnetic field applied on the sample. Uh, Now you have to also remember that the sample I am talking about all this time is only for paramagnetic sample, because in the starting of the explanation of adiabatic demagnetization, I explained that the sample has to be paramagnetic for this process to happen. Okay, so this is the main crux of the MCQ question that is asked. So you have to always remember that the sample is paramagnetic, not something else. Okay, so now let's say this is for h equal to 0 case. Now if a field which is, let's say, h1 applied, the entropy of the system in presence of a field is lower compared to entropy at field equal to 0. Because you can see in this graphs that if you take a particular temperature, let's say you are here at this temperature, and you draw a straight vertical line to see where you land up in the two curves. So for h equal to h1 you are here, okay, your entropy is lower. But at the same temperature, when you are at h equal to 0, that means 0 field, then your entropy is higher. So basically you can get to see that with a field application, even at the same temperature, your entropy is lower compared to 0 field process. And why should that happen? That is also very natural, because you have a paramagnetic sample. So paramagnetic in abbreviation I am writing as PM. So you have a paramagnetic samples where the spins are, when no field is applied, the spins are all randomly oriented. So they have no particular order. So the overall magnetization or net magnetization is 0. Okay, that is the explanation of paramagnetic sample you are already familiar with. But as soon as you apply a field which is non-zero, so in presence of field H1, the spins in the paramagnetic sample will tend to align parallel to the, so this is the parallel sign I am taking, so parallel to the field H1. Okay. So because of that, there will be introduced some partial order in the system, not even if not fully, because there will always be some real temperature instability that is present in the system in real systems, but there will be a partial order that will be effective in the system. So partially ordered system, and this happens due to the magnetic field that is being applied. So naturally, if there is some partial order that is generated, so the randomness will decrease, and in other terms the entropy decreases at h equal to h1. Okay, so this is the initial idea. And now based on this, let's say let us look at how it is used for cooling down mechanism. So let's say when initially there is no magnetic field and you switch on a magnetic field around the sample. So obviously the sample will start to get magnetized, and as we see from the entropy graph, that as soon as it starts to get magnetized, that means it will go from 0 field to a finite field value where it will get magnetized. So this is from A to B, let's say. In this process, its entropy is decreasing, right? So when field applied, entropy at B point is less than entropy at A point. So entropy is decreasing. That means your DS, the change in entropy between initial and final process, is negative, because final entropy is lower than initial entropy. So DS is negative. So here the work done, the magnetic work done in this case, okay, so it will be compensated in some terms of TDS term, which is dq, which is negative in this case because ds is negative. And in the adiabatic demagnetization setup, there is a mechanism that is there, that when this kind of work is magnetic work is done with ds negative, that is compensated in terms of heat exchange with the surrounding. That, I mean, in up to that term, up to that part, there was no adiabatic condition that was applied, and this gets compensated. This means magnetic work done because of the entropy change, or in the other terms because of the magnetization change, because you have applied a field, so H is non-zero and your magnetization has changed. Basically from zero magnetization you have got a finite magnetization, so this is the work done, magnetic work done, and this gets compensated by exchanging heat dq with the environment. So at this step here, at this step the process is not adiabatic. Rather it's isothermal. Why isothermal? Isothermal means the temperature is unchanged. Isothermal because if your dq compensates your dw, then you have no change in internal energy of the system itself, so du equal to 0. And if the system internal energy is just the same, then the inherent temperature of the system, so the temperature of the system is constant, so it has no change. So that means it is an isothermal process, and not, because dq is not equal to 0, heat is being allowed to being exchanged, so this is a non-adiabatic process. Now this part it was fine. Now the next step is that after you have magnetized the paramagnetic sample, now you slowly turn off the magnetic field that was externally applying magnetic field around the sample. Now slowly switch off the external magnetic field edge vector. So now the paramagnetic sample where the spins were aligned because of the presence of the field, paramagnetic sample now starts to get demagnetized. That means it will again start to, like the spins that are earlier aligned in the field direction, when the field is also turned off, so again the spins will be randomly oriented with no particular alignment. So the paramagnetic sample now starts to get demagnetized, and in this process, whenever you are going from this H equal to H1 finite field step to again going back to the H equal to 0 case, so the reverse process, let's say this is I and this is the final state F, so you are going to a higher entropy because then there was no field present. So that is in this case going to a higher entropy, going to higher entropy, that is more disordered system. Obviously because the spins are again trying to get randomly oriented with no presence of magnetic field. So in this case, like the final entropy is greater than the initial entropy, so your ds is positive. And here we restrict the setup to be adiabatic. That means no heat exchange with the surrounding, with the system and the surrounding is allowed. The system is not able to exchange heat with any part of the surrounding, so dq is strictly 0. So because of this demagnetization, this HDM magnetic work done has to get compensated from somewhere, because this is the energy conservation rule, right? So this is the magnetic work gets compensated, because it cannot get compensated via dq like before, because dq is strictly set at 0. Okay, so the only way to compensate the magnetic work done is through the system's internal energy du. And in this case, if your dq equal to 0, then your du plus dw equal to 0. So your du equal to minus dw, minus of the work done. And this work done is basically the magnetic work done, and we will eventually find out mathematically that this du is negative. That means the internal energy is actually dropping down, and as a result, internal energy drops, and as a result the temperature is decreased or cooling occurs. Okay, so this is what I was trying to give you a rough idea of how the system actually works for cooling in adiabatic demagnetization. Now if you look at the setup design, it will be easier for you to just grasp the idea that I was trying to tell you. So setup configuration, just how the experimental setup looks like in reality for the adiabatic demagnetization cooling. So basically you have a dewar field of liquid helium. Sorry. So basically you have a dewar field of liquid helium. So I am making a double wall dewar, but there can be multiple walls present. So basically to isolate the liquid helium from the environment so that it does not evaporate or condense it out with the heat exchange from the environment, so the dewar should be properly insulating with multiple walls. So this is a dewar flux in which there is liquid helium present. So let's say this is liquid helium level, and this is a liquid helium bath in which the temperature is the helium liquid temperature, which is 4 Kelvin initially. And inside this there is a like container sort of enclosure is put down. This is an enclosed container within which you have your paramagnetic salt samples placed. So this is your P paramagnetic salt sample, and on both sides of this, between this gap of the in the gap between the sample and the container in which it is enclosed, there is a gas medium that is present, by which I am denoting by G. G is basically helium gas that is filled inside the container around the paramagnetic sample salt. Okay, and here you have a valve to open or close, and in this it is connected to a pump. And similarly, this dewar chamber is also connected to a pump. I'll tell you why these pumps are required later, but this is the dewar. Okay, and the most crucial part of this system is that in both sides there should be powerful magnets that are placed. So let's say I am drawing it in this shape. So the shape can be better. Let me try. This is a magnet, and this is basically another magnet. So this is basically a north pole and south pole of a magnet, between which the total sample with the dewar flux and liquid helium bath, everything is present. So this is the magnet that is to apply your external magnetic field. These can be electromagnet, or these can sometimes also be superconducting magnets to generate even higher magnetic field values. Okay, so this is your dewar with insulation in the wall. This is your liquid helium bath initially at 4 Kelvin, because that is the melting point of liquid helium. There is a liquefaction point of helium. But later on, this pump that is attached to this dewar, you can see this pump. So this pump actually helps to pump out whatever, because this is a liquid helium, so this is not completely stay liquid, but some part of it will evaporate out eventually, and those helium vapors will be remaining on the top surface of the liquid. So this pumping method is a very well known and effective and easiest mechanism, I would say, to reach lower temperature. So basically this pumps actually sucks out the helium vapor, whatever helium vapor is accumulated on top surface of the helium liquid bath. And because of this continuous pumping, this actually takes the helium bath to even a lower temperature. I mean from 4 Kelvin, which is the natural liquid helium temperature, because of the additional pumping method, it cools down the helium bath to around 1 Kelvin. So by pumping out the helium vapor on top surface of the liquid helium bath, temperature is further lower down to at least 1 Kelvin. Okay, and after this 1 Kelvin reached, then the initial temperature condition of this adiabatic dehydration to start actually satisfied. So after that you do is whatever after you reach 1 Kelvin in the bath itself, and you have to also remember that this sample, parametric sample that is placed inside this container, around it there is a helium gas medium, right? So that is basically working like a convective medium. So it is basically helps in convection mechanism to transfer cooling or heat between the liquid helium bath and the sample. So the convective medium between the sample, parametric sample P, and the environment, which is in this case the liquid helium bath, is your helium gas, because it is filled with helium gas. So because of that, if this outside helium bath is cooled down to 1 Kelvin, then because of this convective cooling transfer, the inside sample will also be around at 1 Kelvin temperature. So at 1 Kelvin temperature, both helium bath and the sample inside. And how that happens is because of the convection of the helium gas that is placed inside this container and the sample P. So when the sample is initially at temperature 1 Kelvin, so what we do is that we now turn on or switch on the magnets. So it will apply an external magnetic field around this area where the sample is also placed. So because the sample is paramagnetic, so now the spins of the sample will try to align in the direction of the field. And as a result, you know that the entropy will decrease compared to the earlier case when the field was 0. So in this case, the magnetic work done that is being done is actually being balanced by the heat exchange with the surrounding, right? So if in this case the magnetic work done in the magnetization process of the sample, so the paramagnetic sample gets magnetized by the application of field H. So it has a magnetic work done of HdM, which is equal to your dq. So some dq amount of heat is generated to compensate that, and that is getting absorbed by the surrounding, which is the bath in this case, and the heat is getting transferred by the gas medium inside, helium gas medium that is denoted by G inside. So getting absorbed by the bath, which is the environment in this case, and as a result the system's internal energy remains unchanged. So du, the change in internal energy, is equal to 0, and your U equal to constant. The total internal energy of the system is constant, or the temperature of the system remains constant. So this is isothermal process, this up to this state. Now after this happens, so now pump out the helium gas from the sample container fully. So if this helium is pumped out, that means there will be no convecting medium between the system and the surrounding, or the parametric sample and the liquid helium bath. So if this gas is pumped out, then that means there is no convection that can happen. If now we slowly turn off the magnetic field, then because of that again some magnetic work will be done, because again there will be a magnetization change and entropy change or an entropy increase. So Then the magnetic work done is at the cost of the changing internal energy du. Why? Because when you have no convective medium, that means you have isolated all connections between the sample and the surrounding, so your dq equal to 0. That means now you have forced it to be a adiabatic in a adiabatic state, and at the same time your magnetic work done is getting compensated in terms of the internal energy change of the system, which is du. Du is not equal to 0. So in this case your dt becomes negative, which you will see shortly that your dt becomes negative or temperature cooling happens. And in this process, if you repeatedly do the same steps again and again, then you can go from, let's say, 1 Kelvin starting point to some lower temperature, and again by repeated method from that temperature to even lower temperature. And by this it is experimentally found out that you can go up to, let's say, 3 millikelvin or 1 millikelvin type of temperature by these cases. So there are samples on which experimentally these are proved, parametric samples, and by this it is said that it can be able to, by repeated cooling method, by this adiabatic demagnetization process, you can go down to at least millikelvin range. Okay, so now you get the main physical idea of this. Physics aspect is clear, I hope. And just for the sake of, let's say if you want to know the mathematics of the calculation, in the mathematical formula or the theory that is behind this physics idea is that this is somewhat happening because of a term called magnetocaloric effect. Okay, so this is somewhat of an display of magnetocaloric effect. Now if you want to explain it mathematically in terms of laws of thermodynamics, then you have to go for the second TDS equation of thermodynamics. So basically here you have to consider that your entropy is a function of both temperature and magnetic field. So generally you may remember that you take entropy to be a function of, generally as a function of T or V, or in some cases as a function of T and P. But here instead of P or V, because you are in a magnetic system, we will introduce B, which is the magnetic flux density, or in other words magnetic induction. So S is a function of both T and B. That means your ds equal to del S del T B constant dt plus del S del B at T constant dB. Now ds equal to, so TDS equal to T del S del T at constant B dt plus T del S del B at constant T dB. So this first part you are familiar with, that this is the specific heat or heat capacity definition, that this T times del S del T, where the conserved or constant variable here is B, magnetic field. So you write it as heat capacity as constant at constant magnetic field is CB. So it is CB dt. Like you have CV dt or CP dt, where they would mean respectively heat capacity in constant volume and heat capacity in constant pressure. Similarly, here we write down heat capacity at constant magnetic field. So basically this is TDS equal to CB dt. Plus now also for Maxwell's equation involving entropy and this magnetic field and magnetic flux density, so magnetization. So Maxwell's equation will show you that this del S del V at T constant equal to del M del T at B constant. So you can replace it here directly. So it is dm dt at B constant dB. Okay, so now so this is your dq equal to all these things. Now it is said that the convective medium is removed. That means there is no heat exchange possible with the surrounding, or dq equal to 0, which is the norms of a adiabatic process. So by this method, so Cv dt equal to minus T del m del T b dB, or in other terms dt equal to minus T by Cv del m del T b dB. So you can see the temperature is decreasing in this method. So dt is negative. Okay. So now we are able to show also mathematically that how this is happening, that actually we are by this principle we are getting a lower temperature or cooling of the sample. And the example being, we can go from 1 Kelvin to 3 millikelvin in an iron, ammonium, alum parametric sample, and some other group has reported to go from 1 Kelvin to 1.4 millikelvin with chromium and aluminium alum. So these are the standard things where you can see that it is actually like getting cooled down by the adiabatic demagnetization process. Okay, so this first part is done. This has become a bit elaborate, but I think the discussion is helpful to for us to understand better in the system. Okay, and now the second question is that Pauli susceptibility is there are separate options. So Pauli parametric susceptibility is we know that it is independent of temperature. So I think this is covered in the lecture material, that Pauli parametric susceptibility is something that is parametric, but it is still not temperature dependent like Curie or ever, etc. So it is basically a independent of temperature susceptibility value. So like let me go to the second question. So we know that if you want to draw the susceptibility curve itself, so this is chi susceptibility versus temperature. So normally your Curie law goes like this. So this is chi equal to C by T. So this is a Curie parametric susceptibility which has this kind of 1 by T temperature dependence. So Curie's parametric susceptibility. And then for diamagnetic case, you have again a temperature, strongly temperature independent value, which is not so huge like not so dominant like Curie's term, but it is a negative value because here diamagnetism means the spins align in the opposite direction of the field. So that is why your chi is negative. So this is negative, and this is the weak diamagnetic contribution that is inherently present in any system, and it is negative susceptibility in the system. So this is diamagnetism with a weak I mean the strength of the diamagnetism is not very much in a system. Okay, and similarly you can have Pauli parametric susceptibility can be somewhere here, but it is also a constant line, it has no temperature dependence, you can see. So this is Pauli paramagnetism or Pauli parametric susceptibility, because this is positive, so it has to be paramagnetic because it has a positive chi, and it is temperature independent, we can see from the graph. And similarly of almost the same strength as the diamagnetic strength, there is a on the positive side there is a constant part that is coming, so which is called as Van Vleck paramagnetism. Okay, so the answer here that is asked is that what is the temperature dependence of the Pauli parametric susceptibility. So the chi of Pauli parametric susceptibility has an expression somewhat like 3n by 2 kb Tf into mu b squared. Here you can see there is no direct temperature dependence. Tf is the Fermi temperature, but that is again a constant value, depends on the material. It is not direct temperature dependent, but it is a constant value that is characteristic of the temperature. So this is 3n by 2 kb Tf mu b square, which is actually the whole expression of Pauli paramagnetic susceptibility, and it is temperature independent. It is positive, weak, that means that it is not as much strong as the Curie susceptibility value. This is positive and weak, and this is a paramagnetic behavior. Okay, so this is the case. And so basically for Pauli paramagnetism also we can solve this a little to actually show that it is actually temperature independent. So Pauli's paramagnetism. This mainly happens in metals having free electrons, where the free electron spins have some effect on the spins because of the magnetic field that gets applied, and the energy band of the system, actually atomic energy band, actually gets splitted in terms of spin up and spin down electrons separately. So basically it comes from the electron spin under the effect of a magnetic field in a paramagnetic sample. So here, for the sake of simplicity, we consider that there is no temperature fluctuation present in this case. So it is like ideal zero temperature range. That means you have everything up to Fermi level is occupied. So this is Fe, the probability of an electron being in the energy state of E, and this is the energy axis. So this is 1. You know the Fermi direct distribution, you know this idea that up to this is 1, and this is your EF value. So this is the Fermi energy EF. Below EF, your total probability of the electron occupying the E state is 1, and above EF the probability is 0. So here Fe is 0. And this is for ideal case, that is at zero temperature, where there is no extra temperature smearing effects. But obviously when there is a finite temperature in actual practical samples, this actually smears out to give you a curve like this, where it is not totally 1 in the entire energy range between below EF, but rather it decreases slightly and smears out like this, and even above EF it is not that the electron cells are completely empty from the electrons or F equal to 0, but there is some finite electron occupancy that is present there on the this term, even if we consider that as I was saying that this is not a zero temperature case, but this is for when you have a finite temperature. So this is, let's say, at T equal to T1, which is not equal to 0, and this blue sharp curve of Fe is for T equal to 0. Okay, but for here Pauli paramagnetism scenario, we will not consider the temperature smearing effect because of the simplicity of the calculation. So we will assume no temperature smearing out effect. And if we want to look at the band diagram, how the spin up and spin down bands will behave when you apply a magnetic field. So basically, let's say this is our G versus E graph. So in the y-axis you have E, in the x-axis you have your density of state Ge. So this will be like a parabola like this, and this is your Fermi level, let's say EF, and this is, let's say, your spin up band, and this is your spin down band. So this is your moment is mu up, and the second term moment is mu down, and up to Fermi level everything is occupied, all the states are occupied with electrons. Now when there is no magnetic field present, that means H equal to 0, so there are equal number of density of states for each spin band. So spin up band has half of the DOS, and spin down band has the rest half of the density of states. Okay. So in this case, if they have equal number of states for both spin up and spin down, then let's say the number of states in spin up case is n up and the number of case in spin down case is n down. So you have basically the total magnetization written as n up minus n down multiplied by the standard unit of magnetic moment, which is the Bohr magnet and mu b, is equal to your net magnetization, which is equal to 0. Okay, so this is the case, and if now we apply a magnetic field in this case, that is B not equal to 0, so how the energy levels will get shifted? First of all, as initially with B equal to 0, there was process like this with this EFL. Now when the field is applied, so the spin up band gains additional energy, or there is an energy shift, positive energy shift because of this field expression, and spin up band gains energy from the field of the amount of plus mu b b, where mu b is the Bohr magnet. Okay, and to compensate that, because the total density of state in the system is fixed, so if spin up has a greater or increase of the energy of plus mu b into b, then the spin down electron energy reduces by minus mu b b. So the mu b b part is same, but here it is minus because spin down electrons energy will be decreasing. Okay, just 1 second, there is some technical issue with the thing, so let me just start again with pausing after some time. Okay, yeah, so let me continue. Sorry, there is a technical problem. So as I was saying that, so when there is a field applied, so obviously initially the spin up and spin down states are with the same number of density of states. You can see that both are on the same level. So if the total density of state is so total number of states is n, then n by 2 number of states are in positive like up spin band, and in a rest of the n by 2 number of states are in the down spin band. This is fine. Okay, and this has a uniform Fermi level also present. But as soon as you apply a field which is non-zero, there is an energy shift for that happens differently for spin up band and spin down band. That will eventually lead them into getting splitted into two bands. So from a uniform single band, you get splitted into two separate bands, which is one is spin up band and the other is spin down band. And that happens because of the application of the magnetic field. Because this was the initial case, like this drawing I have done is for B equal to 0, right, as you have seen earlier. So this is your spin up band and this is your spin down band. Now as soon as, let me take a different color. So as soon as you apply a field, the spin up band's electron will gain, the energy will increase by plus mu b times b, because that will be getting favored by the magnetic field, because let's say our magnetic field is in the upward direction. Okay, and your spin band of upward spin band will get favored by the magnetic field because that is in the same direction. So as a result, its energy will increase by plus mu b times b. But because the spin down electrons has a down spin and that is in the anti-parallel direction of the magnetic field, so its energy will be decreasing by this minus mu b times b amount. So if this is the line initially, so then now the new line will be like, let's divide this from, this is a 0, right, this is the origin, this is your energy, this is your density of states axis. So now this half, the on the left side of 0 you have spin up band, so now its energy will be shifted up parallelly at a new point with a positive offset of plus mu b B. So this shift from 0 to this point is plus mu B B, and the spin up band has got shifted because of the application of the field at B not equal to 0. At the same time, if you look at the other half of the graph, which is denoting the spin down band this side, and it will be shifting downwards because it has an energy decrease of minus mu B B. So initially if the band was here at 0, so now it will be parallelly getting shifted to a new point where it ends up at minus mu B B, because now the energy offset from the initial position is mu B B in the downward direction. So now if you just look at what is the position, so this is again, let me write down, this is again for B not equal to 0 in spin down band's new position. Okay, so now if you can see that there is a total offset of 2 mu B times B, which is basically the energy difference between the two spin bands, because one spin band has gone up by plus mu BB and the other spin band has gone down by minus mu BB. So the net energy difference that has happened, or that had made the band getting splitted from each other, is 2 mu B times B, which is evident. Now in this scenario you can see there is no matching between the, how can you define the Fermi level of the system, because you have to reach some kind of equilibrium of the system, right? So to reach a equilibrium in the system and get a uniform Fermi level throughout the two bands, what happens is that your electrons are getting transferred from this upward shifted band, that is the spin up band. Basically its energy band will be now getting shifted higher. So let's see this. So from here the spin up electrons will now getting transferred into, this spin down band. All right, so electrons get transferred from here to here, so electron transfer. And why that happens? Because throughout the system you need a equilibrium position of the Fermi level, and after this renormalization and all the electron transfer and equilibrium is when is reached, so then you have a band configuration something like this. Let me draw it. So there you have here, and this is, sorry, this is up to here. So this is your spin up band and this is your spin down band. Okay, and so basically you have a uniform Fermi level now defined, because this is a single line Fermi level crossing through both the bands, because it has reached now a thermal equilibrium. This is the case for B not equal to 0, when there is a non-zero magnetic field present. So there is an energy shift splitting the two spin bands, and the energy difference, or the difference between these spin bands in energy axis, is 2 mu BB. Okay, so this is how the bands have been renormalized after the equilibrium is reached, and you have a constant line of the Fermi level EF here. So this is your energy axis E, and this is similarly your density of state axis G. Okay, so now we have to calculate the magnetization ultimately for this Pauli paramagnetism susceptibility formula. You have to calculate each of the, like for say spin up bands total number of states you have to calculate, and similarly for spin down bands total number of states. And after that, from that expression, if you multiply that by mu B, you will get the magnetization value, and by taking a derivative of magnetization with respect to field, you will get a susceptibility value. So that is our idea of doing this. So the number of states in spin up band equal to n up. Okay, so how that is defined? Formula is it is half times Fe G of E plus mu BB into dE, where this limit and energy goes from minus mu BB to the Fermi level EF. So this we mark, this is the minus mu b level. Okay, and this is where the this spin band, the down spin band ends, is the plus mu b level. So basically these bands have been renormalized from this location to this location. Not renormalized, I have to say this is readjusted so that it has a uniform Fermi level. And this is the position. So for spin up band, you see that its starting point is minus mu b in the negative axis, and it can go up to the EF level. Similarly, for the spin down band, it starts from plus mu b energy axis and then goes up to EF, which is the Fermi level. Now we can take the assumption here that the mu b energy shift is very much smaller compared to the Fermi energy. Okay, so assume mu b is very small compared to the Fermi energy EF. So by the assumption, you can take that this mu b value goes to 0 almost. And you also assume that this Fermi level is has a much higher order value compared to any other energy scale present in the system. So by that assumption, if you take the that is what naturally happens in this kind of systems, that Fermi energy level is basically naturally at a much higher energy level, and with respect to the Fermi level energy, other energy scales in the system are really negligible. Okay, so based on that assumption, we can take this Fermi level energy value going to infinity. This is for the simplicity of the integration, otherwise you cannot have a closed solution from this integration, right? And how is this formula defined? So basically this is your density of state expression GE. Now this is for GE plus mu BB, because this is for spin up band, your energy is increased by mu BB. So this is the modified density of states for the spin up band. And you know that density of state basically defines the number of states per unit energy interval and per unit volume in a system. So in this case, we are like excluding volume from the expression, because we are considering for simplicity that the volume is unity. Okay, so you do not have to bother about volume, only you have to take account for the energy interval when you take the integration, so that you can get the total number of states. So basically you have to integrate out the density of states G E plus mu BB in a DE interval, but there is also additional term of Fe, which is basically the probability of the state E getting occupied by the electron. Now this you have also to consider, because for fermions this comes from the Fermi-Dirac distribution function. So you do not necessarily just cannot have the states present, but also you have to consider whether the state is getting occupied by the electron or not. So that is why the term Fe appears in the expression in the integration, and the energy range of the integration is obviously from the starting and the ending point of the energy band, from minus mu BB to EF, which is simplified from 0 to infinity limit. And this half factor is coming because as I said initially, that initially when there was no field present, both spin up and spin down band are equally present, like they have equal energy, and also they have equal number of density of states. So in that sense, whenever you take this separate count of number of states for these two bands, you have to take a half factor to take account for the half of proportion for the two spin bands initially. Okay, so this is why this is coming, and this is getting simplified to half 0 to infinity f of epsilon g of e epsilon plus UBB d epsilon. Okay, so this is your A now. Similarly, the number of states for the spin down band, if you have to calculate similar way, so half factor, and here the lower limit will be coming from plus mu BB up to EF, and which will again be simplified to infinity, and this will be simplified to 0, and this occupancy factor Fe. Then the density of state modified for spin down band is GE minus mu BB, because here the energy gets reduced by mu BB factor, and then D. Okay, now as I said, you have to calculate the magnetization, net magnetization of the system, that is nothing but the Bohr magneton mu B multiplied by the number of state in spin up band minus number of state in the spin down band. Okay, so now you have to simplify these expressions so that you can get the integration done. So here we take use of the Taylor series expansion. Okay, Taylor's expansion. If you remember Taylor's expansion, it is basically says that f of x plus h can be broken down into a series form like f of x plus h f prime x plus h square by 2 factorial f double prime x plus so on and so forth. Here the assumption is that h is very small. Okay, just 1 second. Okay, so assumption is that h is very small so that you can expand it in a Taylor series like this. Similarly, our density of state expression where g of E plus mu b b, you have already assumed that this energy scale is very small. Okay, so we can expand it in a similar Taylor series expansion. How? It's basically that you have GE plus mu b times b, which works like h in this term, into G prime E, which is nothing but your first derivative of G with respect to E. So let us write it as dg dE, plus we will ignore the higher order terms and we only truncate the series up to this. Similarly, for GE minus mu BB, this density of state can be series expanded like GE minus mu BB dGE E plus other higher order terms. So if this happens like this, then the integration will be easier, that n up minus n down equals to half integration limit from 0 to EF. FE is common factor in both of them, so take FE as common. Then GE plus mu BB minus G E minus mu BB into D. Here it is half 0 to EF FE. Now if you just take a subtraction of these two series expansions, so you see that the first term it cancels out because this is common in both of the series. Only the second term is of the opposite sign. So if you take this minus this, then this minus and minus makes it plus. So you have 2 mu BB into dGD. So you have 2 mu BB G D. Okay. So now this half factor and this 2 cancels out. Mu BB is constant, so comes outside the integration. And you are left with the integration looking like 0 to infinity FE dGD D. Now you can take integration by parts. Okay, that will make it easier. So integration by parts mean you have FE dGD D from 0 to infinity minus dF dE, derivative of the first term, and then the similar integration of the second term, and the whole thing is taken inside another second integral, again going in the limit of 0 to infinity. Now we have to understand here that in the first term mu BB, this FE is multiplied, so this is dGD into D, means this integrates out to simple GE, right? So GE, the whole thing is taken inside the limit of 0 to infinity. And the second term is dF dE. Again, this integration gives you G. So dF dE G D from 0 to infinity. Now the simplification gives you that the first term will go to 0. Why 0? Because your density of state G, electron density of state, goes to 0 at the lower limit E equal to 0. At 0 energy there is no density of state present. So that is why at 0 energy you get G equal to 0, and that is why the whole product at the lower limit goes to 0. Now at the upper limit, which is at infinity, even if G at infinity cannot be 0, but F at infinity at E tends to infinity, this Fe tends to 0. Why? Because this is the Fermi-Dirac distribution function, gives you the electron occupancy in the states. So this you know from the formula, that from the general expression is that if this is Fe and this is the energy axis, then this is 1 for all the states below EF, and all the states that are above EF, Fe is 0. So even if your energy is at infinity, your Fe value will be 0. As a result, the whole product will be 0. So basically both for the upper limit and the lower limit, this product term, the first term actually gives you a 0 value, or it vanishes. So you are only left with the second term. Now the second term will also have, you will also have to use some simplification. First thing is that you know that if this is the Fe form, so this is like a step function, right? Step function at EF. Now the derivative of step function, you know that that is a Dirac delta function. So it is already standard that your derivative of the step function, in this case your f function df/de, if you plot with respect to E, it will be a negative delta function. So it will be like delta of E minus EF, because the Dirac delta function is occurring at E equal to EF. The peak is occurring at E equal to EF. So except for at E equal to EF, it shows a Dirac delta sharp peak, and all other points that is away from EF, the value is 0. So if you replace the Dirac delta functional value in this, so to separate it out, so this is mu b minus term comes, so it is 0 to infinity delta of E minus EF. Now this is minus delta because this is a negative delta function that is coming as the derivative of dfd. So this minus and this minus cancels out, makes the whole thing plus. So delta E minus EF GE D. Now you know the rules of Dirac delta, how it works. So whenever there is a multiplication of this function with this Dirac delta function with the point, the central point being EF, and this is within the limit of 0 to infinity, so it will be reduced to simple G at EF. So this is the density of state at the Fermi level. Now this you are getting the value of N up minus N down. Now your magnetization is this term multiplied by mu b. So if you multiply mu b with this term, you get, just we will directly write mu b squared GEF to B. Net magnetization for this system, where the spin bands are getting splitted by the application of magnetic field, which is the main starting idea we started with in this problem. And if you have to get to susceptibility, the chi value is basically m by h. H is the external magnetic field. If you have to get in terms of B, you have to multiply a mu naught in both numerator and denominator. So you have mu naught m by B, because B equal to initially mu naught times h. Now just replace the value of m here. So this is mu naught mu b squared GEF, and this B and B cancels out. So this is the final value of chi. Now you know this is a separate calculation, but this is a very standard calculation in solid state or condensed matter, that what is the density of state at the Fermi level. It is basically 3n by 2 EF. N is the number density of electrons, electron number per unit volume, and EF is the Fermi level. Or in other terms, you can also write this EF as Kb times Tf, where Kb is the Boltzmann's constant, Tf is your constant Fermi temperature. So the whole expression of chi Pauli susceptibility equal to mu naught mu b squared Bohr-Manhattan squared 3 into electron density divided by 2 Kb Tf, as I had written earlier. So as you can see on this whole expression, there is no dependence directly on temperature. So this is temperature independent, as was asked in the question. And you also see that this has a positive sign. That means it is a paramagnetic susceptibility. Okay. So this is the explanation of the Pauli paramagnetic susceptibility and why it is temperature independent, as I have solved the derivation for you, so that you can get the idea why I am calling it just paramagnetic also, that it is coming as positive, and why it is temperature independent. So this question is also solved. Now the later on questions are not, I will not go into further details because these derivations are elaborate and it took a lot of time. So that in the next discussions we'll just briefly cover the idea, and if you have some doubt in any of the derivations, you can explicitly ask that, and I can solve the derivation for you. Okay, so the number 3 question is that provided that only the ground state is occupied with appreciable probability in thermal equilibrium, the overall magnetic behavior of a material containing ions with a shell 1 electron short of being half filled is determined by, there are 4 options given and you have to choose the correct option. First, let us understand the question part by part and break it down into few parts and try to understand what is being asked in the question. Okay, so it is said that the ground state is being occupied with appreciable probability in the thermal equilibrium. Only the ground state, that means no excited state is present, so only the ground state is being occupied. And the overall magnetic behavior of the material containing ions with a shell 1 electron short of being half filled. That means if the total capacity of a shell has some like if you, let's say for F shell you have seven separate parts and each part can contain 2 electrons maximum. So you have total capacity of 14 electrons for F shell, right? Now F shell being half filled means you have 7 electron. That means your F shell is half filled. Half filled F shell. And in the question it is being asked that your electronic configuration is 1 short than half filled. That means if it is F shell, then it has not 7 electron but 1 shorter than that. So that means it has 6 electrons. Similarly, if it is a, let's say P shell's maximum capacity is 3 into 2, which is 6. That means half filled, being half filled means it has 3 electrons, and 1 short from being half filled means it has 2 electrons according to this question. Now we have encountered this kind of a concept in just the starting of the week 6 lecture. You can find it out yourself that in such a scenario, when this kind of a scenario is given, just 1 second. So in this kind of a scenario, mostly you can calculate and see that your total angular momentum J is 0. Okay, so your J is 0. For example, you can choose any of the examples over here. That, let's say, let me choose a page separately. Why I am saying that J will definitely be 0, because depending on that we have to decide which contribution of magnetism will be dominant. Okay, so for 1 less than half filled electron shells, your total angular momentum J becomes 0, but your individual values of the orbital angular momentum L is not 0, and the spin angular momentum is also not 0. How that is happening? Let us take an example of a P shell which is less than 1 shorter than half filled. That means it has 2 electron present. So how it will look like? Basically P shell has the 3 compartments and you have 2 electrons. So 2 electrons means it is 1 shorter than 3, which is 1 shorter than being half filled. And if it is P, that means this is 0, this is minus 1, this is plus 1. So if you have to calculate what is the L for this case, L is basically sum over ml mod. So this is minus 1 plus 0, which is basically 1. So L is 1 and that is not equal to 0. Similarly, what is the total spin angular momentum? Basically 2 separate electrons, both of up spin. That means it is 2 times half, which is again 1, which is again not equal to 0. So L and S are individually not equal to 0. But because it is less than half filled, so the rule is, Ohm's rule is that your total angular momentum is calculated by mod of L minus S. So which is mod of 1 minus 1, which is 0. Thus, you can take example of any shell like S, P, D, F, any shell, and if you apply the condition that your shell is less than 1 less than being half filled, you can separately calculate their L and S value and also the J value, and you will see that the J value will come as 0. And so if your J is 0, then just remember that energy perturbation expression that you learnt in the lectures. So you had learned from the perturbation theory, if you encounter the different terms in the energy correction, you have first term goes like mu b times n L plus gs n. In this case only ground state is occupied, so your n is basically your ground state denoted by 0. And the second term was sum over n prime not equal to n mu b L plus gs n prime, this whole thing whole mod squared divided by en minus en prime, plus there is a third term coming from the diamagnetic term, Larmor's diamagnetism, that is independent of any spin or angular momentum component. This is 8 e squared by 8m d squared in xi squared plus yy squared in. So the first two terms are paramagnetic contribution and the last term is diamagnetic contribution, which is known as Larmor's diamagnetism. Because this is, you can see this has no contribution from either L or S. So no L or S dependence. So it does not depend on unpaired electron. It comes inherently in a system. Okay, so it is an inherent contribution present in any system. Inherently present. But this is of course a very weak contribution. It only gets dominant when you have the other two terms going to 0. And when the other two term goes to 0, basically when your L goes to 0 and if your L goes to 0 and S goes to 0, then obviously the first term goes to 0 and the second term also has this term. So this whole term, first and second, goes to 0. First and second term are 0. So only diamagnetic third term dominates. Okay, third term dominates the magnetic property or decides the magnetic property. And obviously if L and S are 0, so if L equal to 0 and S equal to 0, then J is obviously 0 because J is nothing but either L minus S mod or L plus S. So in either way J is 0. But in our problem this is not the case which is given. In our case, in the question, just let me plug it inside the charger. Okay, so in our case, our J equal to 0, the total angular momentum, but L is not equal to 0 and S is not equal to 0. So by that mean, you can see that the expectation value of, this is basically the total angular momentum J, because the G value, Landau G factor can be 1. So if J is L plus S, then this is the entire value of J, and between these two states, N, which is in this case ground state 0, you have basically the expectation value of J, which is calculated in the first term. So if the J value is itself 0, then obviously the expectation value of J with respect to the ground state is also 0. Okay, so then first term vanishes. Okay, but in the second term you see that you have this L plus gs, which will give you the angular momentum J, but it is not the expectation value you are calculating over here. You have to operate that operator on a separate state which is not ground state, that is n prime, and then you have you have to take the sandwich with a ground state n. So this is basically not a direct expectation value, so it will not give you a 0 value if J equal to 0, because you have L not equal to 0 and S not equal to 0. So even if J equal to 0, the second term does not vanish. Second term non-zero, because there you are taking terms like this, n prime not equal to 0, then this is the 0 state taken as n state, and here L plus gs, then this is n prime, this is en, E0 minus en prime. Okay, so this term is not vanishing, and this is called your Van Vleck susceptibility term, Van Vleck magnetization term, and this is paramagnetic because this will be a positive contribution to magnetization or susceptibility, so it is paramagnetic, and this is very weak. Okay, so this will only also be effective in the case when the first term is 0. So then only we can see the effect of this Van Vleck term. Okay, and the third term, which is the basically Larmor's diamagnetic term, is independent of all three, that is no L, no S and no J. So even if L and S are not non-zero and J equal to 0, or even if all of them are 0, this third term is ever present because this is the inherent property, diamagnetic property of the system. So that means in our case when J equal to 0 but L and S are non-zero, the first term is vanishing, this is going to 0, the second term is non-zero and the third term is non-zero. So the second term is our Van Vleck term, Van Vleck paramagnetic term, and the third term is our Larmor's diamagnetic term. Okay, so basically your total magnetic contribution is coming from the competition between these two terms. So you have to choose the answer that it comes from the difference between, let me choose the option. So the option number 2 is correct, that it comes from the difference between the Larmor diamagnetism term and the Van Vleck paramagnetism term, because those are the only two terms that survive even at this condition. The first term will vanish, that will not have any contribution. So option number 2 is correct in this case. Now question number 4 is that the NMR experiment, NMR means a nuclear magnetic resonance experiment, involves a resonant absorption of which ray by nucleus. So the answer will be, it is a radio frequency radiation that is used in the NMR experiment. So I'll just briefly explain you the idea of NMR, that in NMR you consider the nuclear spin. Okay, so the nucleus also has an effective spin, and when there is a magnetic field present, that spin tries to precess around this magnetic field direction, or eventually it will try to align along the magnetic field direction. Now when it gets aligned, that means it gets ordered. After that, you if you just give the system, expose the system to a radio frequency pulse of radiation, that means you are basically exciting the system to go from the lowest energy state or the ground state to the excited state. So that means the ground state was the state when the spins were getting aligned, in the nuclear spin were aligned in the field direction. Now you are exposing it to a radio frequency pulse. That means you are exciting the system, you are increasing its energy to go into the for the nuclear spin to go into an excited state. But because it is a pulse, so once the pulse is gone, so the system will again try to go back to the earlier ground state value, because that is a stable configuration. That means the nuclear spins will again try to align along the field direction. So in that process, it will come to from the excited state to the ground state by re-emitting the radiation in the RF frequency range. And in this emission process, it has some resonance in a particular frequencies, and at what frequencies the resonance will appear depends on the molecular structure of the material. So basically, by looking at the like noting down the RF frequency or RF intensity that is being emitted from the material after the radio frequency pulse is gone, and if you note the data over time, so let's say if your RF intensity data, it will decay over time obviously. So if you note the data over time, this is your RF radiation intensity that is emitted by the molecules, radiation emitted intensity. So if you note the data over time, then if you take a Fourier transform or FFT of this data, so you will get a particular resonant frequency peak at a particular frequency. So this is frequency axis, this is, let's say, F1. So this is the resonant frequency for this emission peak to appear. Now there can be multiple resonant peaks to be appearing from a system, like from here, here and here. So let's say F0, F1 and F2. So By identifying these resonant frequency values F0, F1 and F2, you can get to know the exact molecular structure of a system. Like say for ethanol, if you have CH3, CH2, OH in ethanol. So for each of them, like for CH3 you have a particular resonant frequency peak, for CH2 you have a separate resonant frequency peak, and for OH you have another resonant frequency peak. So just by noting down the radio frequency that is emitted in the process of getting down to ground state from the excited state, the resonant frequency peaks will show exactly what is the molecular structure of the material. And radio frequency radiation is the radiation that is actually comparable to the gap between the energy levels of the nuclear spins that the nuclear spins occupy. So that is why the radio frequency emitted radiation is needed when you try to excite the nuclear spins from its ground state to some excited state, and in terms of that further you note down the time series intensity measurement. Okay, so the answer is radio frequency. Now question number 5 is a mathematical question. It says that the electromagnetic frequency range required to probe crystal field splitting energy, which lies in the range from 12.5 MeV to 2.5 electron volt, is approximately given by, you have to get the answer in the frequency range. So this is very simple. You have the energy range in electron volt, you have to get the frequency range. So you know the basic relation. I'll just write down it here. So you know that E equal to h nu. This is the relation between nu, the frequency, and E, the energy. And h is the Planck's constant, which value is universally known to be this, also given in the question. Now only thing you have to take care of is that your energy values are given in electron volt unit. You have to convert them into joule unit so that these units can match with each other, because in the H you have joule per hertz, right? So you have to consider all in the same unit. And other than that, everything is just straightforward formula. So basically, if your E2 is 12.5 MeV, that means 12.5 into 10 to the power minus 3. Now convert into in joule. So electron volt to joule means you have to multiply by another factor of 1.6 into 10 to the power minus 19. This is in the joule energy value. Similarly, E1 is simply 2.5 electron volt, that is 2.5 into 1.6 into 10 to the power of minus 19 joule. And if that is the case, then your nu2 is just E2 by H, and nu1 is just E1 by H. In terms of H, you put the value of 6.626 into 10 to the power minus 34. So this joule per hertz, and in the top it is joule. So by cancelling out from that unit, you get nu in the hertz unit, and you can use your calculator. I have used mine, and the answer is coming as, I think the first option was correct. Yeah. So the answer will be in the order of 10 to the power 12 hertz. Okay, so 10 to the power 12 hertz means 1 terahertz. So terahertz is equal to 10 to the power 12 hertz, and the answer is coming as 3.02 terahertz to 604 terahertz. Okay, so the answer should be exactly matching to this. If not, then maybe you have not considered some extra decimal places. If you exactly consider all the decimal places up to at least third decimal place, like in this Planck constant it is given up to third decimal place 626, so then you can get this exact solution by just directly using this formula of frequency to energy conversion. Now question number 6 is again a conceptual question, I think. It is said that which of the following statements is true. Let us read them one by one and try to understand whether that is correct or not. And the first question is that derivative of free energy with respect to magnetic field of a magnetic material is 0. This is a false option. Why? Because you know that if F is the free energy, then your del F del H is nothing but your magnetization M. That means the first derivative of the free energy with respect to the magnetic field is nothing but the magnetization. And for a magnetic material, the magnetization is always non-zero. So that means the first option is not right. That the derivative of free energy with respect to magnetic field, which means your magnetization of a magnetic material, it is saying that will be 0, but that is not true. So option 1 is not true. Similarly, second option, look at second option. It says that for an ion with J not equal to 0, the Van Vleck diamagnetic susceptibility is dominant, where J is the total electronic angular momentum. Now this we also have studied in the Van Vleck susceptibility term, but here this is a printing mistake. This should be paramagnetic because Van Vleck is not a diamagnetic term, it is a paramagnetic term. Now for an ion with J not equal to 0, this will not happen, because for J not equal to 0, if you remember that your first term of L plus Gs will be much more dominant, and that will basically suppress the second and the third term. Both the Van Vleck in the second term and the Larmor's diamagnetic term in the third term will be suppressed if your J is not equal to 0. You can only get an effective Van Vleck paramagnetic term if you have J equal to 0 but L not equal to 0 and S not equal to 0. So basically Van Vleck, that is the second term in your energy correction delta En. Van Vleck is only effective when J equal to 0 but L not equal to 0 and S not equal to 0. So first term will vanish, the most dominant term, first term will vanish, and the next dominant term will be the second term, which is our Van Vleck term. So this option number 2 is also not correct, because here it is said that for J not equal to 0 Van Vleck will dominate, but it is for J equal to 0 that it is dominant. And not only J equal to 0, but you have to ensure that J equal to 0 with L and S are non-zero. J equal to 0, L not equal to 0, S not equal to 0. Now the third option is that following the Hund's rule, J is 0 for n equal to 6 and n equal to 14 for the F shell, where n is the number of electrons in that shell. So this we have to calculate by the shell configuration by drawing that whether J equal to 0 or not. So let us also read the last option that we'll do it next, but also read the last option, that the susceptibility in Curie's law is always temperature independent. This is obviously false, because you know that the basic Curie law says that chi is C by T. C is the Curie constant and T is the temperature. So obviously the Curie susceptibility is inversely proportional to temperature, but option number 4 says that it is temperature independent. So it is false. So this is false, this is false, and this is false. So most obviously option number 3 will be the only true option. But for the consistency check, we will also calculate the value whether it is really coming as J equal to 0 or not. So let us go to the blank page. So this is our question number 6. It says that first of all, let's take the case for n equal to 6 electrons in the cell, and you have a F shell, right? So F shell has 7 compartments, 1, 2, 3, 4, 5, 6, 7. So by following Hund's rule, how the electrons will be filled up? So this is important, that if you have gone through the Hund's rule in the week 1 lecture, so I will not elaborate that again. So if you have 6 electrons, that will be filled like 1, 2, 3, 4, 5, 6. And the compartments have this ml values as 0, plus 1, plus 2, plus 3. And here minus 1, minus 2, minus 3. These are all the ml values for the compartments. And so your total angular momentum from the orbital angular momentum is sum over ml mod, which is equal to minus 3, minus 2, minus 1, plus 0, plus 1, plus 2. Now this minus 2 and minus 1, plus 1 and plus 2 cancels out, and if you are only left with L equal to 3. Now S, the spin angular momentum, is half into 6 electrons, that means 3. So now you have J equal to, now these are 6 electrons, that means F orbital has half filled, to be half filled, in F shell you have to have 7 electrons. So you are in 6 electrons, that means you are less than half filled. So by following Hund's rule, your J expression is mod of L minus S. So that means it is mod of 3 minus 3, which is 0. So this is true that J equal to 0 when F orbital has n equal to 6 electrons. Now the second thing was also given, that when n equal to 14 electrons, whether similarly we can get J equal to 0 or not. So if n equal to 14 electron, again draw the F shell by yourself, that is 1, 2, 3, 4, 5, 6, 7. So this is minus 3, minus 2, minus 1, 0, plus 1 plus 2 plus 3. The electron filling in will be, first of all the shells, all the compartments will be filled with one up spin electron first, and when it is totally completed, then the second occupancy will appear. So like this, in the opposite spin you have total 14 electrons. That means this F shell is completely filled completely. So obviously in such a case your L is mod of ml, which is nothing but this 2 into, because there are 2 electrons in each of the compartments. So this is minus 3 minus 2 minus 1 plus 0 plus 1 plus 2 plus 3. So this whole term is 0. So this is 0. L is 0. Now your S is, now in each of the compartments you have one spin up electron and one spin down electron. So that net spin in each of the compartment becomes 0. So if you have, even if you have 7 compartments totally filled, you have 0 into 7, that is 0. And again in this case your J equal to L plus S, or if you can also take mostly L plus S. So 0 plus 0 is 0. That means in both the cases, as the option said that J will be 0, it is correct. So our option number 3 was indeed correct, while the other options were false, as we had already discussed. So it is done. And then question number 7 is also a similar Hund's rule type of a problem, where you have to calculate the term symbol for the GD3 plus ion, which has an electronic configuration like this. So let us say that GD has this configuration already given to you, right? So if you have to take GD3 plus, that means you have to eliminate 3 electrons from the outer orbitals, which leaves you with 4f7 only, because this 6s2 2 electrons and 5d1, total 3 electrons will be gone. So only up to 4f7 you are remained with for GD3 plus. Now for the term symbol you have to again draw a cell structure of the last cell. So it is an F shell. So this is 1, 2, 3, 4, 5, 6, 7. So if you have 7 electrons, that means 1 electron in each cell, and the shell is half filled. 1, 2, 3, 4, 5, 6, 7. So this is 0, plus 1, plus 2, plus 3, minus 3, minus 2, minus 1. So you have to calculate what is the L value. L value is summation over ml mod. So each electron occupying one of the compartments, so the total net summation will be 0. And S is half for each of the compartments, and total 7 compartments. So this is basically half into 7, which is 7 by 2. So if L equal to 0, you know that happens when the term symbol becomes S, capital S, because you probably remember that L equal to 0, 1, 2, 3, 4 and further ahead. So 0 is plus capital S, 1 symbol is P, then 2 is capital D, for 3 the symbol is F, for 4 it is G, and similarly H, I, J, etc. So for L equal to 0 you have to use the symbol of S. Now the term symbol has like this 2s plus 1, where this s is the orbital angular spin angular momentum s, and this s is the term symbol s. So both are different. And in the subscript you have G. So this is the rule of writing this. Now so this is just, if s is 7 by 2, then 2s plus 1 is just 7 plus 1, that is 8. And your J is, you are getting, so this is half field. So we know that for less than half field it is L minus S mod, and for greater than half field it is L plus S. But for half field both will be held. So I mean both the option will be correct. So using any of that, L equal to, let's say, J equal to, let's say we'll use L plus S. So this is 0 plus L is 0, so 0 plus 7 by 2 is 7 by 2. Or you could have also used J equal to mod of L minus S, then also it will get the same answer, because it is half field, so any of the rule will apply. So this is 7 by 2. That means if you have the term symbol as 8S, 7 by 2, which is the first option. So option number 1 is the answer in this problem. Now question number 8, again you have to get the, according to Hund's rule, you have to get the number of effective Bohr magnetons. So the initial process is same, only you have to know what is the formula for Bohr magneton. So basically Bohr magneton is the effective magnetic moment, effective total magnetic moment divided by the magnetic moment for equivalent to the Bohr magneton. So basically effective Bohr magneton is the count of the number of Bohr magnetons present in the total effective magnetic moment in the system. So effective Bohr magneton P is equal to nothing but the net effective magnetic moment, which is mu effective, divided by the value of each Bohr magneton, which is mu B. This gives your value of the Bohr magneton effective count P. So let me go to a separate page. Question number 8. First of all, you have to know the formula of mu effective. Mu effective is the effective magnetic moment, which is J plus 1 into J. This is under square root into mu B. This is a well-known expression. You can find out the derivation from the lectures. So if this is the case, then mu effective by mu B is nothing but Gj into root over of J into J plus 1. So this is what you have to calculate. For that you have to know the values of Gj and J, right? So Gj is your Landé G factor and J is your total angular momentum number. So, and this Landé G factor also has a formula. So we will use that. Landé G factor's formula is Gj equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So your Gj value can be calculated if you know the separate values of J, L and S. Okay, so to know the J, L and S value, you have to consider what is the Nd3 plus electronic configuration. So your Nd was given as xenon or total field, then 4f4, then 6s2. So Nd3 plus means 3 electron has to be eliminated out. So this is xenon. So this 6s2 will be gone and 1 electron shorter from this. So this will be 4f3. So what will be the structure of 4f3? So this is 4f shell, 1, 2, 3, 4, 5, 6, 7. So fill up 3 electrons. This is 0, plus 1, plus 2, plus 3, minus 3, minus 2, minus 1. So your L is sum over ml mod, which is minus 3, minus 2, minus 1. That is 6 plus 6. And your S is half into 3, which is 3 by 2. So your J will be, now this is less than half field because half field for F shell is 7 and it is 3 electrons in the F shell, so it is less than half field. So by following Hund's rule, your J is mod of L minus S, which is mod of 6 minus 3 by 2, which is 9 by 2. Okay, so you have got all the values of L, S and J. Now you just have to put the values in this expression formulas and you will get Gj and you will also get this last value. So just use your calculator. Now you can also get what is the term symbol for this Nd3 plus. So your L value is 6, right? So you know that for L equal to 0, 1, 2, 3, 4, 5, 6. For 0 it starts with S, term symbol, then 1 it is P, 2 it is D, 3 it is F, 4 it is G, 5 it is H, 6 it is I, and so on alphabetically. So here the term symbol for L equal to 6 is I, then 2s plus 1 to J. And if S is 9 by 2, that means 2S plus 1 is simply 10. So, oh sorry, right, S equal to 9 by, sorry, S equal to 3 by 2. I forgot, J equal to 9 by 2. So, your S, 2S plus 1 is 2 into 3 by 2 plus 1, that means 4. So, here it is I 4, then J is 9 by 2. This is your term symbol, even if this was not asked in the question, but I still have solved it. So, right. Now just use your calculator and get the value of Gj by substituting the values of J, L and S. So you will get your Gj comes as approximately 0.72. Okay. And now using this value, you get P equal to Gj value is 0.72. Then substitute the J term here, J into J plus 1 square root, 9 by 2 into 9 by 2 plus 1, and we get exactly approximately the value of 3.62. So this is your formula answer. So this is I think option number 4. Let us check whether option number 4 has 3.62. So yeah, so option number 4 is correct. Now only 2 questions are left. So question number 9 is that when a ferromagnetic material is heated above its Curie temperature, then it becomes, so this is very simple. You know that in ferromagnetism you have a Curie temperature below which the material is ferromagnetic or perfectly ordered, even in the absence of a field. But beyond this Curie temperature, the system becomes paramagnetic. That means it has a weak magnetism. The spins are randomly oriented from each other. Only if you apply a magnetic field, they will get aligned along the magnetic field direction and give you some non-zero magnetization. Otherwise, the magnetization will be 0. So this is very simple. That this is your Tc. Then above Tc, this is just a paramagnetic behavior proportional to 1 by T behavior. And for below Tc, when it is ferromagnetic, then it has, sorry, this is not perfectly drawn. You can also check Google for the drawing. Okay. Here this is going like proportional to 1 by T, and here this is ferromagnetic behavior is different. Sorry, the drawing is getting messed up. But I hope you get the idea that here this is a different curve that is followed for the ferromagnetic part. Okay. So these are not continuous like they are appearing over here. So these are the different curvature from this. This is Tc. So similar to this. So this is Tc. Beyond Tc it is paramagnetic, and below Tc it is ferromagnetic. Okay. Sorry, and this was in the y-axis, this was chi, and the x-axis was temperature. Chi and temperature. And the very last question is also mathematical. It says that a paramagnetic sample shows a net magnetization M, let's say it is M1 of 8 ampere per meter when placed in an external magnetic field of 0.6 Tesla. Let's say your magnetic field B1 is 0.6 Tesla at a temperature T1 of 4 Kelvin. When the same sample is placed in an external magnetic field of 0.3 Tesla, that means your B2 is 0.3 Tesla, and at a temperature of 8 Kelvin, which is your T2, then what will be the magnetization? That means you have to get what is the value of M2. And hint is that you have to use the Curie's law of magnetization. So the hint makes the problem very simple for us to solve, because you know the Curie's formula of paramagnetism, right? So just recall that. Let us recall that in one line. That you need. I need not go through all the derivation. You can go through the derivation in the lecture series. So Curie's law of magnetization says that your magnetization M goes like small n UV square B divided by KBT, where N is the electron density, UV is the Boltzmann B is the magnetic flux density, KB is the Boltzmann constant, and T is the temperature. So apart from the other terms which are constant, and maybe for the same sample the n will be constant, so that will not be something that will be bothered about, but we have to get the relation between m, b and t. So here we'll directly see that m is directly proportional to b, but it is inversely proportional to t according to Curie's law. So by that form, your m2 by m1 will be b2 by b1 into t1 by t2. So your m2 is equal to m1 into b2 by b1 into t1 by t2. Now just put the values of m1, b1, b2 and t1, t2. Your m1 was 8 ampere per meter. Then your b2 was 0.3 Tesla divided by b1 0.6 Tesla into t1 was 4 Kelvin and t2 was 8 Kelvin. So this is half, this is half, and this 4 and 8 makes it 2. So you get 2 ampere per meter is the answer of your m2. So you get that your magnetization for this case will be 2 ampere per meter. So let us choose the option. So it is right. Option number 2 is correct because it has 2 ampere per meter. So with this we are done with the week 2 tutorial session. Now these problems that we have solved will probably be helpful for you. Now if you have any doubt regarding any question, you can ask me in the next session, and let us finish the tutorial here.